Hi, in this video we'll talk about ARMA model identification. And by model identification, what we're talking about is not the estimation of the parameters of an ARMA PQ. That is, we're not talking about any longer trying to estimate the fees for the AR side or the thetas for the MA side. What we're talking about instead is how many of those fees are there, how many of those thetas are there. In other words, what's the value of P, what's the value of Q. So that's the basic idea of what we're going to do. Now we're going to talk about two different types. One is called the AIC type method for identifying P and Q. And the other one is called the pattern recognition method. And that was developed by Box Jenkins, very famous book in 1970, a classic time series book, and that's called the partial autocorrelation function. That's actually not going to be useful for ARMAs, but for ARs only. So if you're okay to let Q equal 0, then that second type of method to calculate P comes into play, and that is the partial autocorrelation function. So let's get into the R code and we will illustrate that. It's really pretty neat, and it's going to be very straightforward as far as the code goes. You'll see in the text that some of the calculations, especially for the partial autocorrelation, gets a little bit involved. It's developed by the Ewell-Walker method, and we'll talk about that soon. But let's jump into the code. All right, so QR64, that's where we're at, Chapter 6, ARMA model identification. Let's look at example 1. We're going to have 3 different examples for the first type. That's the AIC methods. Then we'll have one example for the pattern recognition. That is the partial autocorrelation function. So here's example 1. And what we're going to do here is we're going to generate a realization from a known model. We do this quite often, right? When we're practicing, we like to use a realization from a model we already know. Like we know this is an ARMA 3-1. And not only that, but we know the coefficients. The fees are 2.57, negative 2.5, and 0.92. The theta is 0.92. Mu is 30, and seed number 65. Okay, so here is our first effort to estimate the P and the Q. So here's how it happens. Well, we use this handy function, this TSWGE function called AIC.WGE. Then the first argument is the data set name. Then you say what you would like your P's to possibly range from. We pick 0 to 12 here. There's nothing special about 12. It's just a rule of thumb. You'll see that pretty often in our text. 0 to 12. And let Q go from 0 to 4. Same thing. Nothing special about 4, but it's just a good rule of thumb. Good place to start. Notice that I've copied that line in the next line of code, and all I did was add type equals AIC. Well, it turns out that those two lines are equivalent because the default for just saying nothing at all is type equals AIC. Now, I've not gone into detail about AIC. If you'll look down the code here, you'll see an AIC, a BIC, and an AICC. So here's a great place to describe those really quickly. AIC stands for Aikiki Information Criterion, and the next one is the BIC, which is the Bayes Information Criterion, and AICC is kind of a hybrid of the two. I'll call it that. But let's go back to the AIC. What do all 3 of these methods do? Well, really their goal is to minimize the error variance. That's the goal. So we want very small AIC values, BIC values, AICC values. We want those to be small because we want that error variance to be as small as we can get it. Now, but here's the thing. A lot like R squared in a regular multiple regression, you can drive R squared up if you'll just keep adding independent variables to the model, if you'll recall that. Well, same kind of thing holds true here. You can drive your error variance down if you'll just keep increasing the order. So obviously there needs to be some type of penalty imposed, and that's what happens. Now the difference between AIC, BIC, and AICC is that they impose that penalty a little bit differently. Some are more heavy than others. Okay, that's what this thing is doing, and that's how it picks its P and Q. All right, AIC. That one is a good one. It's a classic. That's the default, so it must be the classic. But one thing that's bad about it is that it's known to pick a higher order than it has to. Maybe a higher order than it should in some cases, especially when the realization is long. So that's the negative on the AIC. So BIC, that's Bayes information criterion, comes along and really penalizes even more heavily than AIC does, and therefore you'll see in our examples and in all cases, I don't know about all, but most cases, the BIC gives a lower order than the AIC. And that's important to note. AICC kind of sits in the middle and is a compromise between the two. All right, now, given that, let's run this first line here. We've generated an AR31. And then what I'm going to do next, I'll go to the third line because remember lines 2 and 3 mean the same thing. Okay, so let's go here. Let's run this line. And remember what we're doing. We're saying, hey, TSWG, help us out here. Look at ARMA 3.1. Look at that data set. I'm going to let you pick from P from 0 to 12, Q from 0 to 4. I want the type, the estimation type, to be AIC, IKEKE information criterion. Give me your best guess at what you think P and Q should be. So let's run that. Notice the delay. It kind of pauses. It's doing some, why do you think it's pausing? It's not pausing. It's working hard. We've asked it to do a lot. We've asked it to look from P equals 0 to 12 and Q from 0 to 4. It finally finished. And now let's see what our result is. Here's the result. We've got several things coming out of this. Look at the $P and the $Q. That's what holds the value of P and Q. It looks like it has chosen a 3-1. And remember, it did not know what we knew. We knew a couple of minutes ago that we were generating an ARMA 3.1. But the model didn't know that. It just looked at this data set and said, I think you're a 3.1. So that's good. It did the right thing. And then also below that, you see the phi coefficients. There are 3 of them. We're not surprised because that's the P part. And there's 1 theta coefficient. We're not surprised because that was the Q part. So good job there by the AIC command. Let's now look at what happens when we look at the BIC. Now remember, we'll run both of them at once. Remember, we're expecting this one to possibly have a lower order because remember, it imposes a heavier penalty on going too high on the order. So let's see what AIC says about this. It says that P is 2 and Q is 0. So yes, it did give a lower order for both the P and the Q. Let's check out AICC. Whoops, I missed it. Give it a second. Takes a little time. It's running through all the different possibilities. And here's its answer. AICC says it's a 3-1. So AICC agreed with AIC, but they both disagreed with BIC. And that's a good little starter example. Let's do another thing. Remember that this AIC.WGE command gave the top choice for the order P and the order Q. We also have another function called AIC5 that gives the top 5 choices. So let's run through that real fast on the same set of data. We'll skip line 1 because again it's the default. It's just the same thing as this one, AIC. It's working, please wait. And now remember, we're expecting this first one to be 3-1, right? It's already told us that its top choice is 3-1. So really all we're wanting to know is, I wonder what the next 4 are. So there's our 3-1, there's a 4-0, a 5-1, a 2-2, and a 3-0. So that's AIC's top 5 choices of the P and the Q. Notice the AIC values. It looks like, of course, they're going to be increasing. Because why? Well, 3-1 is the top choice, so that must be the lowest variance. Anything after that must be increasingly, right? Okay, that is AIC. Let's go to AICC. I know that's a little bit out of order as the way that we did it first. AICC, remember these agreed last time, so we're expecting another 3-1 for the first choice. But I wonder how many of the other ones agree with between AIC and AICC. And here it is. Looks like it says 3140 and then 305122. So they didn't agree on anything after the first two. So that's interesting. They're just different. The penalty is imposed differently. The formula is different. You can see it in the textbook. You can see the formulas. They're not crazy hard, just a little bit different. You can see how they're certainly different from one another. It may have been hard to derive them. I would suspect it probably was, but you can take a look at that if you would like. Let's now do the top 5 of BIC's choices. We know what its first choice is. It's 2, 0, but I wonder about the other 4. Working, please wait. Here it comes. 20, 30, 21, 31, 40. So differences among them. That's example 1. Let's look at example 2, which is going to be on a real data set. The very famous, we've talked about it before and read about it before in the text, the links data. So data links, we'll look at the log links like we often do. Remember that the reason we would like to do that transformation and take the log transformation of the links data is it smooths out the variance. The variance of the links is quite erratic. There's some really high peaks and some low troughs, and the log of that links data makes the variance more constant. So that's why we do that. We'll run that. There won't be any output. We could plot it if we want, but we've done that in the past. Let's do the same thing that we did before. Let's do an AIC on this. We won't give a type, which means that it'll be AIC. And let's see what happens when we look at when we ask AIC 5 to give us its top 5 favorite picks of the links data. And we get high numbers, 12-0, 11-1, 11-0, 11-2, 12-1. It's a complex data set. Let's look at AICC. (12-0, 11-0, 11-1, 11-2, 12-1). So some pretty consistent agreement there between AIC and AICC. Now let's try BIC. We're expecting these orders to decrease quite a bit, and there's plenty of room for it since we're in the 12 and 11 range. Let's see how much BIC is willing to go down. 2-3, 3-3, 2-0, 4-3, 2-1. So pretty interesting. Didn't even get, there was no 5 in there even. So BIC definitely holding up to its reputation of not liking to go to a very high order. And remember, there's some value in that. We hear a lot about the word parsimony. Parsimonious models mean more simple models. Sometimes a more simple model is better than one that's complex. And by complex, I mean just lots of parameters, lots to deal with, and sometimes it's more attractive. I guess it's always more attractive for a smaller model. By smaller, I just mean fewer parameters. But there's some value to that, so parsimony counts. So BIC is something to certainly think about. All right, the next example is example 3, and this one is going to be another generated realization from an AR3. This is called A_real, and we illustrate this in a previous example, and we're also going to talk about it in our partial autocorrelation function in the example right after this. But this is our last example of using AIC methods. We're going to generate this realization, and it's going to be an AR3. That means we'll have 3 phi coefficients. There they are, 1.71, negative 1.22, 0.475. And let's run that. It will go ahead and plot it as well. There's your realization with that particular seed of this AR3. So we know the answer. We know that this is a P of 3 and a Q of 0. Let's see if our AIC and AIC5s pick that up. So I'm just running 2 here. We'll run an AIC on the data set, P going from 0 to 12. Let's not even give Q a chance, although that would have been interesting to see if it would have been fooled to pick up a Q. I didn't do that, but let's see what we're going to have here. Now remember, what's the default? I've not put any extra arguments in there, so this probably looks a little short to you, but the reason is because the default type is AIC and the method is MLE. Okay, so let's run it and see what happens. And it picks P equals 3, no Q in sight, so it must have picked a Q of 0. There are the 3 coefficients. Let's see how well these coefficients match up. I haven't done that yet with you. 1.76, pretty close to 1.71. Negative 1.40 matches well with negative 1.22. 0.56 matches pretty well with 0.475. So not bad. Let's see how sensitive it is. What if we did AIC 5 and change things up? Let's go to BIC and let's go to method of Berg instead of MLE. Let's see how it does. So we're wondering, is BIC going to get fooled? Because we know it's an AR3. Is BIC going to get fooled and take it lower than a 3? And it did not. It says that we've got a P of 3, and therefore BIC got it right. So there's, it's not like it's always going to give an order that's lower. And in this case, it did the right thing. All right, here's our last example. Remember I said there are 2 types of these model identification methods we're going to talk about. The first was what we just did. There were AIC types. The second is called the pattern recognition method. And again, I told you it comes from the very classic book by Box and Jenkins in 1970 when they defined the partial autocorrelation function. And let me talk about that definition for just a second. What the partial autocorrelation is it's the correlation between 2 time points, ignoring any correlations of anything in between. So what it does is it isolates just the 2 variables, the 2 time points of interest, and says, I want to ignore anything else, any other correlation structure in between us. And that's called a partial autocorrelation function. Again, there's some pretty dense, I guess I would have to admit, formulation in the text on this topic. You can go there if you would like to, but let me show you a really quick and easy way to work this in R, in our TSWGE package. This is all you have to do. Look at, or not look at, give, don't look yet, I need to give the command first. The syntax is PACF, or partial autocorrelation function, .wge, then give the data set. Then take a look at your plot and see if you notice a dropping off of the correlation. So it looks a lot like an autocorrelation function. So here it is when I run that. Notice what happens. We have, first of all, I need to tell you something important here. We're used to an autocorrelation function, that first value being 0 right here. But for a partial autocorrelation, it's actually 1. So this is 1, this is 2, this is 3, this is 4, and this is 5. So again, on an autocorrelation function, that first spike is at 0 and it always goes to 1. But for the partial autocorrelation function, it does not do that. It starts at 1. Now, here's why the partial autocorrelation function can be helpful for you in identifying an AR model. Not an ARMA, but an AR model. So this one is more limited than the AIC methods. AIC methods can identify an AR, an ARMA, or just an MA model. But this partial autocorrelation function is only going to be valuable in identifying an AR model. And here's what happens. We show in a key point in our text that this partial autocorrelation happens to go to 0 immediately following the order of the model. Now that didn't come out right necessarily. I'd need to write that down as a formula, but let me take you straight to the plot and I'll show you what I mean. This was lag of k equals 1. This is lag of k equals 2. This is lag of k equals 3. I'm going to say that this is lag k of 4. I'm going to claim that that goes to 0. Meaning, yes, I had something substantial at k equals 1. I had a PACF that was substantial for lag k equals 2. I also had something substantial for k equals 3. By substantial, I just mean something that's clearly off of the 0 line. This one right here at k equals 4, that one is not far enough off 0. I think that this thing is zeroed out at the 4th lag. And that if a partial autocorrelation function plot plays out, meaning that it zeroes out at lag k equals 4, that is an indication that this model could be modeled, or this data set could be modeled well by an AR3. So wherever the partial autocorrelation function plot zeroes out, the lag right before it is what we estimate as our order of the AR model. So I hope that that's helpful in understanding what we mean in our text by those two different methods. We talked about the AIC type methods, which really includes AIC, BIC, and AICC. And secondly, what we just discussed, that's the pattern recognition method given by Box and Jenkins, which really means go look for the partial autocorrelation function plot and see if you can see that it's clearly zeroed out at a certain lag, and if it is, step 1 lag before it, and that's the order of our P for the AR model. See you next time.